Today we will be learning about the thin layer chromatography technique, and like all chromatography techniques, the separation of compounds is based on how well they would interact between a stationary phase and a mobile phase. For example, in gas chromatography, we had a thin layer of liquid coated on some solid beads as the stationary phase, and we had a carrier gas that served as the mobile phase. And the molecules were separated based on how well they interacted with the liquid phase or how well they interacted with the gas phase. In thin layer chromatography, or TLC for short, it's a solid liquid form of chromatography, whereas in the gas chromatography, it was a liquid gas form of chromatography. And in TLC, the stationary phase is normally a polar adsorbent material, which we call a TLC plate. And the mobile phase can be a single or a combination of solvents. And what happens is that the solvent system will be what moves like the gas in the gas chromatography, so it will be the mobile phase, and the solvent can move along the stationary TLC plate, and in that process it will drag along any compounds that were applied on this TLC plate, and it should be able to separate them into their different components. So TLC is a quick and inexpensive microscale technique that can be used to determine the number of components in a mixture. Like this example image we have here, this compound that was applied onto the TLC plate was actually a mixture of 3 different organic compounds, and by doing a TLC, we were able to visualize that. Or we can determine the identity of 2 substances. If we have a known standard compound and we are expecting that compound to be synthesized in a certain organic reaction when we're doing synthesis, we can run that standard along the product we obtained from the synthesis and compare to see whether we got the correct compound. And the same way we can monitor the progress of a reaction. If we know that halfway through the reaction we are expecting a certain organic compound to form, we can run it alongside its standard and compare their separation on a TLC plate to see if our reaction is going on the correct direction. The stationary phase of TLC is either a piece of aluminum or a piece of glass that has a very thin, very fine coating of finely ground alumina or silica particles. So this would be the solid adsorbent material that would serve as the stationary phase in this technique. The TLC plates that we use for this lab have a coating of a material made out of polydimethylsiloxane. So basically, it's a polymer made of multiple repeats of a dimethylsiloxane. So there is a silicon atom here and 2 methyl groups and 2 OH groups, and we know that oxygen is highly electronegative. So when there is a polymer of this compound, there will be multiple repeats of this oxygen in that material, making that material a very polar material due to the presence of many oxygens. So for the purpose of this lab and this class, we will have to consider that these TLC plates are very polar due to the material that they are made of. There are instances where TLC plates are made of other materials with different polarities. but for the purpose of this class, you don't have to consider them. Please always consider the TLC plate as being very polar due to the material it's made of, which is polydimethylsiloxane. And this material is also mixed with the fluorophore, so when we expose it to UV light, this plate will fluoresce with a green color, and if we have any compounds spotted on the plate, we would be able to visualize them as dark spots. The mobile phase is basically a solvent system which is made of either a single solvent or it can be a combination of solvents. Since the polarity of the TLC plate is considered to be very high, what we can change in our experiment is the polarity of the solvent system. So the polarity of the solvent system can be adjusted by changing the compositions of the solvent mixture. For example, in today's lab, our solvent system is going to be made of 10% ethyl acetate and 90% hexane. Ethyl acetate is a relatively intermediate polar solvent, while hexane is mostly a non-polar solvent. Since this solvent has 90% of hexane, this solvent has an overall non-polar characteristic. But we can change the overall polarity of the solvent system by changing the composition of each of these components in the solvent. If we changed it to 90% ethyl acetate, that would increase the overall polarity of the solvent system and make it more polar. So, in order to obtain a better separation of compounds on the TLC plate, we can play around with the overall polarity of the solvent system and change how the compounds separate on the TLC plate. Basically, the concept for compound separation on TLC would be based on whether the compound applied on the TLC plate would prefer to form intermolecular interactions with the material on the TLC plate, like the dimethylsiloxane, or else would that compound rather prefer to form intermolecular interactions with the solvent system. So if we have a polar compound, for example, and we have a solvent system that is mostly nonpolar, and we know our TLC plate is very polar and it's always polar in relation to the solvent system, the polar compound would be able to form stronger intermolecular interactions with the polar TLC material because like interacts with like. So in that case, the compound prefers forming intermolecular interactions with the TLC plate and would stick mostly to the plate rather than move along across the TLC plate with the solvent. But if we had an instance where the compound was a nonpolar compound and our solvent system was nonpolar mainly, and our TLC plate is always polar in relation to the solvent system. Now, the nonpolar compound would be able to form stronger intermolecular interactions with the nonpolar solvent system than the polar TLC plate because like interacts with like. So in that case, that compound would be able to move further up the TLC plate as the solvent moves along it. So this is basically the concept behind how compounds get separated on a TLC plate. It all comes back to the polarity properties of the compounds and the polarity properties of the solvent system. Now let's take a look at an example to make sure that you understand this concept. Let's say we have a compound mixture made of biphenyl and malonic acid, and we are trying to separate it on a TLC plate that is made of dimethylsiloxane, and our solvent system is made of 10% ethyl acetate and 90% hexane. Let's look at the polarity characteristics of the compound mixture. Biphenyl only has carbons and hydrogens, so basically it's a hydrocarbon and doesn't contain any polar bonds in it, so it's a non-polar molecule. Compared to that, malonic acid has multiple carbonyl groups and OH groups, so due to the very electronegative oxygen, these bonds are very polarized towards oxygen, so that gives malonic acid a more polar property. So malonic acid is a much more polar molecule. Let's take a look at the solvent system. So hexane is basically a six-membered carbon, carbon and hydrogen structure, and it's non-polar. Ethyl acetate has this acetate group and an ethyl group. So compared to hexane, it's relatively more polar, but it also has these non-polar portions on it. So overall, ethyl acetate has intermediate polarity. However, in the solvent system, there's only 10% of ethyl acetate but 90% of hexane. So overall, the solvent system is nonpolar. Now, if we have the TLC plate, remember the TLC plate is always more polar, and we have applied a spot of our compound mixture, and we developed this TLC plate in this solvent system. How would these two compounds separate? Biphenyl, being a nonpolar compound, would prefer to interact more with the nonpolar solvent system, so it should move further along with the solvent, and it would be on the top of, it would separate and move along further than malonic acid. While malonic acid is a polar compound, so it wouldn't be able to form stronger intermolecular interactions with the mainly nonpolar solvent system. So instead, it would be able to form intermolecular interactions with the polar TLC plate and therefore not move that far from the starting point. So the mixture of these two compounds have now separated into their own spots based on their polarity properties and based on the polarity properties of the solvent system. Here I will be walking you along the steps of setting up a TLC experiment. Now, this is a TLC plate, and you should always remember to handle the TLC plates only by touching the edges of the plate. We should avoid touching the surface of the TLC plate even if you are wearing gloves, because we have to assume the gloves might have many types of contaminants on it, and if we touch the surface, those contaminants would get absorbed onto the plate and contaminate the plate, and that would interfere with observing a correct result. We handle the plate only by edges, and then using a ruler and a pencil, we would mark a starting line and a stop line from about 0.5 centimeters from the bottom of the plate and 0.5 centimeters from the top of the plate. And it's very important that we only use a pencil for this purpose, because the pencil is made of graphite, which is an inert material, and this graphite is not going to interact with any of the organic solvents that we're going to use in the solvent system. If you use a pen to draw these lines, the ink in the pen is also a mixture of organic compounds, organic solvents, so they would dissolve to the the solvent system when we place this plate within the solvent system. So we should avoid marking any lines on the TLC plates with a pen and only use a pencil. And the reason is the pencil is made of graphite and it's an inert material, therefore it does not interact with the organic solvents in the solvent system. And we should be gentle when we draw these lines, because the plate is made with a very thin coating of that silica material, either on an aluminum base or a glass plate. So these lines should be drawn very gently, making sure not to scratch off the thin coating of the silica material. Once we draw the lines, we can make some marks on it to evenly space out the compounds that we're trying to spot onto the plate. So how we spot these compounds onto the plate is by using a capillary tube. This is a very thin glass, like little glass straw, and when we insert it into the solution containing our compound, it should be able to draw in that liquid via capillary action. And then we bring it up to our TLC plate, press it on the mark that we're going to spot our compound, and just hold it for like 2 seconds and the spot will be applied. We have to be very careful during this step, making sure that these capillary tubes are very clean, because if there was other compounds contaminating the inside walls of the capillary tube, our spotted compound will be contaminated and we will see other contaminating spots appearing on the TLC plate. So during the lab, we made sure to rinse the capillary tube using some ethyl acetate between each spotting. Ethyl acetate, like we discussed earlier, has an intermediate polarity, so it's able to dissolve many different organic compounds. So if there are any organic compounds contaminating the capillary tube, they should be rinsed off by rinsing the capillary tube with ethyl acetate. Once we apply these spots on the markings that we made, we will check the plate under UV light, and in the UV lamp that we were using, we used the short wave in order to shine this plate in green fluorescence light, and we would be able to see the spots that we applied. We do this before we start running a TLC plate to make sure that the spots are properly concentrated around the markings that we made, and the spots between different compounds are not overlapping with each other, and to make sure there are no contaminations on the other parts of the plate. Once we make sure of that, we place the TLC plate in a beaker containing the solvent system, and it's very important to make sure the level of the solvent system is below the starting line of the TLC plate because we want the solvent to move along the plate. Let me switch to the pen. So we want the solvent to move along the plate. But if the solvent was already above the starting line, then this compound that was spotted to the plate would just dissolve into the solvent and we won't be able to achieve an appropriate separation. So it's very important to make sure that the level of solvent should be below the starting line of the TLC plate. And we let the solvent rise along the plate until it reaches the stop line, and we will use tweezers to pick up this plate out of the solvent. And of course, during the time that we call this developing the TLC plate or running the TLC plate, during this time we usually keep this beaker covered with the watch glass to ensure that this is like a small chamber completely saturated with the moisture of the solvent system, and that makes sure that the solvent rises across this plate at an even rate. It's not going to be like one side rises faster than the other side. We want the solvent to rise at an equal rate all over the plate. So by closing this with the watch glass and ensuring this little beaker is a fully saturated chamber, we make sure that the solvent moves along the plate at a similar rate all across the plate. Once the solvent system reaches the end line, we're going to take it out of the little chamber, allow it to air dry, which is just going to be like a minute. And after that, we will observe it under the UV light, and the plate will shine with green fluorescence, and we will be able to visualize the separated compounds as spots. And using a pencil, we can circle those spots to make sure we mark where the compounds have moved across the TLC plate. And after that, you will be calculating something that we call as an RF value, which stands for retardation factor. If you remember, in gas chromatography, we had something called the retention time. It explains how much that particular compound was delayed as it moved through the column. In TLC, this RF value explains the same thing. How much was this particular compound delayed in its movement across the TLC plate? And that value is going to be unique to each particular compound. How we calculate this RF value would be calculating how far the solvent traveled versus how far the compound traveled. So the solvent would travel from the starting point all the way to the stop point. So this distance across the plate would be how far the solvent traveled. We call it the distance traveled by the solvent front. That's why we have SF. Then for the compound, usually as these compound spots move along the TLC plate, they get a little bit diffused, which is why we have much bigger circle-like spot instead of a very concentrated spot. So we will measure the distance to the middle of the spot from the starting line, and this would be the distance traveled by the compound front. So we call it CF. The RF value would be the ratio we get when we divide the distance traveled by the compound front from the distance traveled by the solvent front. So if you had a standard compound and you were expecting that compound to be the end product of a certain organic synthesis reaction, you would run the standard alongside the end product you got from the reaction and compare the RF values, and if they are the same, then you can conclude yes, the compound that you made from the reaction is what you were expecting for, since you confirmed the RF values to be the same using TLC technique. Can the RF value be greater than 1? This is usually a question that comes up in the exam. So, can this ratio between CF and SF be greater than 1? If you think about it, this is the distance the solvent travels, right? And the maximum possible distance a compound can travel is also this exact same distance. So the maximum distance a compound can travel is equal to the distance the solvent travels. So in that case, CF would be equal to SF, and RF, which is this, and if both of these are the same value, the ratio will be just 1. So the maximum number you can get for an RF value is 1, and it can never be greater than 1. And the reason is the maximum distance the compound can travel is the maximum distance the solvent can travel. In today's lab, we're going to look at the separation of 6 different compounds using the thin layer chromatography technique. So the 6 compounds we're using is naphthalene, 9-fluorinone, benzophenone, 4-methoxyacetophenone, fluorine, 4-nitroaniline. And like we mentioned earlier, the solvent system used for the lab today is going to be 10% ethyl acetate and 90% hexane. The separation of these 6 compounds across the TLC plate is going to be based on their polarity characteristics. If we look at these 6 molecules, which molecule would have the highest polarity? So we're going to try to list them from the highest to lowest polarity. If we look at these molecules, we see that 4-nitroaniline seems to have charged groups in the molecule, right? And charged group means that this molecule is an ionic molecule. And we know that ionic molecules have the highest polarity because they are able to form ionic interactions, which are the most polar and strongest type of intermolecular forces. So 4-nitroaniline would be the most polar out of these 6 compounds. Next, we have 4-methoxyacetophenone, which seems to have 2 oxygen atoms, and by the number of carbons, it's not so different compared to the other molecules. So since it has 2 oxygen atoms in it, it's going to contain 2 polarized bonds. which gives it a higher polarity compared to the remaining other four molecules. So that would be the second most polar molecule. Now we have four molecules left, and we can see that two of them each contain a carbonyl group. And the carbonyl group is going to give these molecules some polar characteristic. However, so how will we determine which one has a slight edge over the other? Benzophenone has fewer carbons than 9-fluorinone, so that means fewer nonpolar groups in benzophenone, which gives benzophenone a slightly more polar property compared to 9-fluorine. So they would be in line to be the next highest polar compounds. Then we're left with naphthalene and fluorine, which are both completely nonpolar, but fluorine has a few more carbons than naphthalene, so its nonpolar characteristic would be slightly more than naphthalene. So on the list from highest to lowest polarity, naphthalene would be slightly ahead of fluorine. And this is our expectation simply by looking at their structures. So if we run a TLC for these six compounds, we would be able to predict their movement or separation across the TLC plate based on their polarity characteristics and based on the overall polarity of the solvent system. Based on our theoretical expectations, this would be the outcome that we are hoping to see once we do this TLC experiment. So I have numbered these molecules from 1 through 6, and this is the order from highest to lowest polarity. Since 4-nitroaniline is the most polar out of this group, we would expect it to interact more with the polar TLC plate than interacting with the overall nonpolar solvent system. So we expect 4-nitroaniline to travel the least distance in this TLC experiment. And in other words, its CF over SF value is going to be the lowest, which means we expect 4-nitroaniline to have the lowest or smallest RF value. 4-methoxyacetophenone is the second most polar compound. Since it's less polar than nitroaniline, it should be able to move across the TLC plate a little more further, but not so much because it's still polar and it still prefers interacting with the polar TLC plate than interacting with the overall nonpolar solvent system. And then you can see benzophenone and 9-fluorinone are able to move further along the plate because they displayed intermediate polarity, so they were able to partially interact with the TLC plate but also equally interact with the solvent system, so they were able to move halfway through the TLC plate. Then we have naphthalene and fluorine, which were both very nonpolar compounds, so they would not be able to form intermolecular interactions with the TLC plate, but they will be able to form stronger intermolecular interactions with the solvent system and move further along the TLC plate along with the solvent system. So they should have higher RF values in the end. This is our expectation of this experiment. So once you record your data, calculate the RF values that has been experimentally obtained for each of these compounds, then compare with what you were theoretically expecting to see. Do they match? Then what does that confirm? What does this trend tell you about the polarity of each of these molecules and how they got separated? So try to make some comments in the discussion about the relationship between the RF value and the polarity characteristics of each of these molecules versus the polarity of TLC plate and solvent system. Finally, I would like to discuss a few technical issues that you should be aware of when performing TLC experiments for this class. Sometimes you might observe that certain spots were all overlapped and smooshed together instead of separating as independent spots. And this would usually be because the spots on the start line were spotted too close to each other. Like I mentioned earlier, these compounds slightly diffuse around as they move along the plate. So although we spot them as a small spot, they become a larger spot as they move across the plate. And if we spot compounds too close to each other at the start line, due to the diffusion, they're going to overlap across each other, and that would affect how they move on the TLC plate. Therefore, if this is what you observe, then that means you need to have more spacing between the samples that you have spotted on the TLC plate. Another issue students may observe is when they look under the UV light, instead of a very clear spot, you see a big smear starting from the spot you spotted on the start line all the way up the plate. And this is usually when this initial sample spot was too concentrated. Either you applied too many times from the capillary tube, or most likely reason is that the sample solution that you used to spot on the plate was too concentrated to begin with. So to rectify this mistake, you will have to dilute your initial sample solution and redo another TLC by applying a smaller amount of the compound on the start line. Another problem students may run into while doing TLC experiments is that they would observe either all the compounds are crowded by the starting line, that none of those compound spots have moved that far across the plate, so there are no significant differences between the RF values, or else all the compounds have moved all the way up to the stop line. So again, there are no significant differences between the RF values for each of these compounds. And the reason would be, let me switch back to the pen. In this example plate, the reason would be all three compounds are polar. That makes sense because they were interacting strongly with the polar TLC plate rather than the solvent system, so they did not move far. And what does this say about the solvent system? It means the solvent system was not sufficiently polar in order to make these three compounds obtain a significant separation. So the solution would be to increase the polarity of the solvent system. Then how about this TLC plate? All the compounds have crowded to the top of the plate. That means that these three compounds are mostly nonpolar, or else the solvent system was too polar. That makes sense because if the solvent system was too polar, now all of the molecules will be able to form strong interactions with the solvent system and move along. But even if this compound was a nonpolar compound, it doesn't have any choice. It doesn't prefer the polar TLC plate. It doesn't prefer the polar solvent system. But remember, the solvent system is always relatively less polar compared to the TLC plate. So regardless, the nonpolar compound will move all the way to the top as well. So to correct this, we would have to decrease the polarity of the solvent system. Now let's say that this solvent system that led to this result had 10% ethyl acetate and 90% hexane. And you would feel like, oh, to increase the polarity, I would make this 90% ethyl acetate and 10% hexane. But this is not a good solution because this dramatically increases the polarity of the solvent system instead of introducing a gradual change. So if you change the solvent system directly to 90% ethyl acetate and 10% hexane, all of these compounds would move to the top of the plate because now the solvent system is too polar. Therefore, a correct adjustment would be rather to make this like 20% ethyl acetate and 80% hexane. So you have introduced a gradual increase in the polarity of the overall solvent rather than a very dramatic change. So this kind of change would be the more appropriate kind of change. So these are actually the different types of questions you would expect in the exam, like you will be given either some technical issues or cases where the compounds did not separate as expected or did not were the student was not able to obtain a significant separation among the compounds, and what would be your solution to rectify that problem. Finally, this slide lists some objectives that you should be able to achieve and fulfill once you work through this lab and finish your lab report. I will have my office hours on Friday, 8:30 to 10:30 a.m. I will post the link for the WebEx session. So if you can come to the office hours, please do so to discuss any questions you have. And if you can't make it during that time, please make sure to reach out through email and I will try to get back to you as soon as possible, and I'll be happy to help to the best of my ability. Thank you.